When using a single machine learning algorithm to map onto a chaotic landscape of real-world data, the model often fails to capture the underlying complexity. To demonstrate this, we can generate a synthetic dataset using scikit-learn's make classification function, 10,000 rows with 10 features. However, only 4 features contain a mathematical signal. The rest are noise. A standard linear model attempts to separate these clusters with a single straight boundary, but because the data is overlapping, it hits a 66% accuracy ceiling. To break this ceiling, we stop searching for one perfect algorithm and instead combine hundreds of weak learners. Applying XGBoost generates overlapping, complex boundaries that adapt to the data's shape. Accuracy jumps to 88%. Reaching this level of accuracy isn't about hyper-tuning a single model. It requires a structural change in how algorithms process data, using either parallel or sequential architectures. The first major architecture is bagging, short for bootstrapping aggregating. It is designed to solve the problem of high variance, where a model becomes so sensitive to its training data that it fails to generalize to new information. As this diagram shows, bagging starts with bootstrapping. Instead of training one model on the entire dataset, we create multiple subsets by randomly sampling rows with replacement. This random sampling ensures that extreme outliers only end up in a small fraction of the training sets, preventing them from skewing the final model. When we use decision trees as the base learners in this parallel chain, we create a random forest. Random forests add a second layer of randomness through column sampling. Using the max features parameter, the algorithm limits each individual tree to a random subset of columns. By blinding trees to dominant features, the algorithm forces them to find secondary patterns. This creates a diverse group of specialists, rather than a fleet of identical models that all make the same mistakes. Finally, new data is run through all these parallel trees simultaneously. The system aggregates their outputs through a majority vote to produce the final prediction. This combination of parallel processing and randomness ensures that individual biases cancel each other out, resulting in a highly robust model. If we rotate this architecture 90 degrees, we find boosting. While bagging uses independent models, boosting builds a sequential chain where each model depends on the one before it. This linear flow is the core of AdaBoost, the foundational boosting algorithm. Every new model is trained to fix the errors of the previous one. The algorithm calculates the error and updates data point weights, giving incorrect predictions a higher mathematical weight. These heavier weights force the next weak learner in the chain to specialize in the hardest edge cases, focusing its information gain on the records the previous model missed. By systematically learning from past mistakes, AdaBoost builds a strong predictive model that neutralizes high bias. Modern gradient boosting takes this a step further. Instead of weighting data points, it trains sequential models to predict the exact mathematical error of the predecessor. The process begins with model 0, a baseline guess of the target average to establish our initial loss. Next, we calculate pseudo-residuals using the negative gradient of our loss function, essentially the difference between the actual value and our initial guess. We then train the next decision tree using our original features, but we set these calculated residuals as our new target variable. Adding this prediction directly to our previous guess perfectly memorizes the training data, causing overfitting. To prevent this, we apply a learning rate. By taking only a tiny fraction of the residual, the model takes conservative steps toward the true value. The loop repeats for several iterations, slowly chipping away at the error, using logistic loss for classification or mean squared error for regression. Gradient boosting is an optimization problem, sequentially building an additive model to minimize loss across the entire dataset. Extreme gradient boosting, or XGBoost, is the refined implementation of this theory. It was designed specifically to overcome the speed and overfitting limitations of standard gradient boosting. XGBoost uses a specialized similarity score to evaluate nodes and employs a gamma threshold to prune weak branches before they are even fully computed. While the math is efficient, the real performance gains come from how XGBoost handles data at the hardware level. To avoid sorting data at every node, XGBoost uses an in-memory block structure, allowing the CPU to evaluate features across multiple cores simultaneously. It also uses cache awareness, allocating internal buffers directly to the high-speed CPU cache to bypass the slower main RAM bottleneck. These optimizations extend to data cleaning as well. XGBoost automatically handles sparse matrices and missing values, deciding the best branch for missing data on the fly. XGBoost works because it integrates statistical regularization with bare metal hardware engineering. We can see these theoretical benefits in practice by benchmarking different models using the California housing dataset. Linear regression is incredibly fast, but its accuracy is poor, returning an R-squared score of just 0.59. Standard gradient boosting improves accuracy to 0.77, but unoptimized for modern hardware, training time spikes over 6 seconds. XGBoost achieves the highest accuracy at 0.83, completing the task in only 0.2 seconds, a fraction of the time. XGBoost's performance stems from re-engineering the training pipeline, proving that state-of-the-art results depend on bridging the gap between statistical theory and computational architecture.